I'd like to give you another example. That is, we're going to try to use as many boundary conditions as we can to find the E field and the potential of a metallic sphere that has a charge Q. So here's the sphere. We have a charge density sigma, which is equal to the charge Q over the area, and that would be the surface area of the sphere. Because what we're assuming is that you put the charge Q on the sphere and it will distribute itself uniformly over the surface. By the way, what you're doing when you do that is you're lowering the local field energy to a minimum by spreading the charge over the sphere. Okay, well, we know the area of a sphere is 4 pi r squared, so this is the charge density. So if we have a surface that has that charge density, a metallic surface, then we know how to get the E field just outside. If we equate these in terms of the charge density, putting that in right here, we can show then that we have this quantity here, sigma over epsilon naught n, is equal to Q over 4 pi epsilon naught r squared n hat. So all we're doing is putting this quantity right here into this equation right here, and remember that this is the E field just outside the metal. If we have r slightly larger than r, then we'll have the E field, which is equal to this quantity here, will be equal to this expression here, which you're familiar with. For spherical symmetry, this is the field of a point charge at r equals 0. If we assume that this is the case for all r greater than capital R, remember E equals 0 for r less than r, then you can write E outside the metal for any r, and that would be the same expression, which is kq over r squared r hat. And remember that r hat is equal to the normal unit vector. So this holds up for r greater than. Interesting thing for us is that if we started with the expression for E just outside, which is sigma over epsilon naught, and then used the constant sigma given by the Q over 4 pi r squared, we can derive then the E field just outside because we have the value of the field in terms of sigma. That's the E field just outside. It's normal. The field is coming out radially from the surface as we would expect. Well, let's take a look at the potential. We're given this E outside, and this holds for any r greater than capital R. We can find the potential the brute force way by using this integral here. So we're integrating the E field from infinity to the position r. And so that's the definition of V of r. Okay, so then when we put in our E, we've done that here. dr is in the r hat direction, so this is dr vector. This is E vector outside. And so simplifying that, we'll have minus kq times this integral here. And if you work that out, you get minus 1 over r. The potential outside is what we might expect for a point charge. It's kq over r. For spherical symmetry, this is the potential of a point charge q located at the origin. So now we use the boundary condition that at r equals capital R, V is continuous. V just inside is equal to V just outside. And the second thing we'll use is the condition that V is constant in a conductor. And the reason that occurs is because the E inside is 0. So if you had a potential that was dependent on R, you would not get 0 because you take the gradient and you get a non-zero value. With a constant V, that will imply then that E inside is equal to 0 and vice versa. V just inside is equal to V just outside. This is the potential outside, and so we set R equal to capital R, and we get the potential just inside. So we're talking about right there, just inside. However, because of 2, V is constant. If you have a potential anywhere inside, then that's the value of V anywhere inside the sphere. We conclude then that V of R inside is just a constant, and so this holds up for less than 0. If we repeat our results then, for the sphere we have V inside equal to this, V outside equal to this. we can see what this looks like. And so we have this value here being this constant right here, and this value here is of course decaying with r like this, so that's this expression right here. And the thing to notice is that if you let little r equal r, then those will be equal, and that corresponds to this point right here. The continuity of V across the interface is shown here. Constant V here is shown here. The dependence of R that we derive right here is this falling off like this. The boundary conditions then are ways of getting these answers almost in an intuitive way without actually doing integrals and things like that. The only integral we had to do was to find V outside by using the integral from infinity to the position little r.